Hello everyone, in this video we're going to explore topic 10.6 comparison test for convergence. Alright, in this topic we're going to explore two theorems. The first one is going to be direct comparison test. This theorem has been proved in the video 10.6a. And the second one is going to be limit comparison test. And this theorem has been proved in the video 10.6b. Now let's take a look at the direct comparison test theorem. Let a sub n less than or equal to b sub n and both positive for all n. If the series b sub n converges, then the series a sub n converges. If the series a sub n diverges, then the series b sub n diverges. I have tip for you to memorize this theorem. If the larger series converges, the smaller series must also converge, right? We look at this one right here, b sub n larger than a sub n, right? So if the series b sub n converges, then the smaller series a sub n converges, right? Now the second one, the smaller series diverges, then the larger series must also diverge. Now we look at this one right here, the smaller one diverges, then the larger one diverges, right? Now let's take a look at the first example using the direct comparison test. Determine the convergence or divergence of the following series, right? So we're going to start with this guy right here. So we have 2 plus 3 to the n, always greater than 3 to the n, right? Now, I'm going to take reciprocal both sides, so it could be 1 over 2 plus 3 to the n. It's going to be less than 1 over 3 to the n, right? So then I have the series 1 over 2 plus 3 to the n when n goes from 1 to infinity less than the series of 1 over 3 to the n when n goes from 1 to infinity, right? Now look at the one on the right hand side right here. This guy can be written as sigma when n goes from 1 to infinity of 1 over 3 altogether to the n, right? And this guy actually geometric series, right? Where the common ratio equals 1 over 3 less than 1. So this geometric series converges, right? Now if the larger converges, the smaller must converge, right? Now question B. Question B is slightly different from question A, alright? So we have 2 plus square root of n always less than or equal to 2 plus n, right? I take reciprocal both sides, so it could be 1 over 2 plus square root of n greater than or equal to 1 over 2 plus n, right? So I'm gonna put the summation in the front. N goes from 1 to infinity. Alright, now I'm going to use U substitution for this one. So that I'm going to use P series, right? This is 2 plus n. I'm going to let U be 2 plus n, right? N equals 1, we have U equals 3, right? N equals infinity, you have U equals infinity, right? So then I have sigma of 1 over U when U goes from 3 to infinity, right? So then I'm gonna shift this one back over here by changing the index, right? So this guy is the same thing as sigma when n goes from 3 to infinity of 1 over n, right? And this guy actually the harmonic series or the P series, right? Where P equals 1 less than or equal to 1. So then this series diverges, right, by the B series, right? The smaller diverges, the larger one must diverge, right? By the direct comparison test. Now, example number 2, we're going to use direct comparison test. So we have n squared minus cosine square of n always less than or equal to n squared, right? I'm going to take reciprocal both sides. So I have 1 over n squared minus cosine square of n greater than or equal to 1 over n squared, right? I'm going to multiply both sides by n. So I have, now I'm going to put the summation in the front. So I have, I'm going to simplify this one. It's going to be sigma when n goes from 1 to infinity of 1 over n. This guy actually the P series, right? Or you can say harmonic series, right? And P equals 1 less than or equal to 1. So this series diverges, right? So the smaller diverges, the larger one must diverge, right? By the direct comparison test, I call this DCT. But on the AP exam, you need to write this one out, right? You need to write this one out. Now, question B. We have n plus cosine square of n always greater than or equal to n, right? Now, I'm going to take reciprocal both sides. So I have 1 over n plus cosine square of n less than or equal to 1 over n, right? Now I'm going to multiply both sides by e to the negative n. So I have, but this guy always less than or equal to e to the negative n, right? So I have sigma when n goes from 1 to infinity of e to the negative n over n plus cosine square of n less than or equal to sigma of e to the negative n when n goes from 1 to infinity, right? Now I can convert this one to the integral. So integral from 1 to infinity of e to the negative s ds, right? Now I'm going to use the integral test. So I'm going to let f of s equals e to the negative s. Now it's easy for you to verify that this function always positive, right? Continuous and decreasing, right? So I'm going to calculate the integral from 1 to infinity of e to the negative s ds equals limit when b approaches infinity of the integral from 1 to b of e to the negative s ds, right? So it's going to be limit when b approaches infinity of negative e to the negative s evaluated from 1 to b. So it's going to be negative e to the negative b, right? Subtract, and it's turned out to be at e to the negative 1, right? So it's going to be limit when b approaches infinity of negative 1 over e to the b, right? Plus 1 over e, right? Now when b approaches infinity, this guy approaches 0, right? So you're going to end up with 1 over e, right? And this one actually a constant. So this guy right here converges, right? Now since this guy converges, this series right here must converge, right? By the integral test, right? Now let's move on to question C. So we have n squared plus 2 over n to the 4 plus 5 is going to be less than n squared plus 2 over n to the 4, right? You can drop 5, right? So this guy can be written as n squared over n to the 4 plus 2, so I have. Now I can simplify this one, so this guy turns out to be sigma when n goes from 1 to infinity of 1 over n squared, right? Plus I can bring 2 to the front, right? So I have 2 sigma of 1 over n to the 4. N goes from 1 to infinity. Observe that these two guys right here are p series, right? Where p equals 2 greater than 1, and this one p equals 4 greater than 1, right? So then these two series are convergent, right? Now each of this one convergent, the sum must be convergent, right? Now since the larger convergent, the smaller one must be convergent, right? So this one converges. Suppose a sub n greater than 0, b sub n greater than 0. If you have the limit of a sub n over b sub n equals L, where L is a finite and positive number, then both a sub n and b sub n either converge or diverge, right? Example number 2 show that the following general harmonic series diverges. So let a sub n equals 1 over a n plus b. Now we're going to compare this one with the p series, right? So the p series is going to be b sub n is going to be 1 over n. Now we're going to take limit of a sub n over b sub n when n approaches infinity, right? So it could be limit of 1 over a n plus b over 1 over n when n approaches infinity, right? Now I'm going to multiply the top and bottom by n, right? So it's going to be limit of n over a n plus b when n approaches infinity, right? Now when n approaches infinity, this guy doesn't really mean anything, right? We can ignore this one. So it's going to be limit of n over a times n when n approaches infinity. This guy cancel out, right? So it could be 1 over a, right? This guy is a constant, right? Now we go back to the limit comparison test, the constant L right here, right? Now since this one right here is the harmonic series, right? And harmonic series always diverges, right? So is this one, right? Now you have helpful examples in choosing an appropriate p-series when using the limit comparison test. Alright, when it comes to this one, you need to use this guy right here. Alright, and this guy actually the p-series where p equals to greater than 1, and this guy converges by the p-series test, right? So if this one converges, this one converges, right? Now for this one right here, we need to use this guy right here, right? And this guy turns out to be 1 over n power of 1/2, right? And this guy p equals 1/2 less than or equal to 1, and this series diverges. So this guy diverges, right? Now for this guy right here, we can drop this guy and this guy, right? We're gonna use this guy right here, right? And we simplify n squared, it's gonna be this one. So this one actually the p series where p equals 3 greater than 1, and it's gonna be converges, right? And if this one converges, this one converges, so they both converges, right? Now example number 3, using the limit comparison test to determine the convergence or divergence of the following series. Alright, so we're gonna pick the series square root of n over n square, right? When n goes from 1 to infinity, right? I call this one a sub n. I call this one b sub n, right? When n approaches infinity of a sub n over b sub n equals limit when n approaches infinity of square root of n over n square plus 1 divided by square root of n over n square, right? So it's going to be limit when n approaches infinity. When this guy divided by this guy, you're going to multiply by its reciprocal, right? So it could be square root of n over n square plus 1 times n square over square root of n, right? Now this guy cancel out, right? So you have limit when n approaches infinity of n square over n square plus 1. So we're going to use relative growth rate, right? So number 1 right here doesn't really matter, right? So we have limit of n square over n square when n approaches infinity, right? This guy cancel out, the answer is 1, right? So this guy actually a constant, right? Now we're gonna go back over here. We check to see if this guy converges or diverges, right? So we're gonna rewrite this one as sigma when n goes from 1 to infinity. This is n power of 1/2. This guy n square, right? So we're gonna simplify this one. It turns out to be sigma when n goes from 1 to infinity of 1 over n power of 3.5, right? Now this guy actually the p series, right? P equals 3.5 greater than 1. So this series converges, right? By the p series, right? This guy converges and the limit is a constant. This guy must be convergent, right? Now question B. We need to use the limit comparison test, right? So we have n times 2 to the n over 4n cubed plus 1, right? This guy is similar to n times 2 to the n over 4n cubed, right? Because when n approaches infinity, number 1 doesn't matter at all, right? And then this guy is the same thing as 2 to the n over n square, right? N and n right here cancel out, right? Number 4 you just ignore it, right? So then we're gonna compare this guy with this guy, right? So we're gonna take the limit of, I call this a sub n. I call this one as b sub n, right? So a sub n is gonna be n 2 to the n over 4n cubed plus 1 divided by 2 to the n over n square, right? When n approaches infinity is the same thing as limit when n approaches infinity of n times 2 to the n over 4n cubed plus 1 times n square over 2 to the n, right? So then this guy cancel out, right? And then you have limit when n approaches infinity of n cubed, right? Because n times n squared is going to be n cubed over 4n cubed plus 1, right? We're going to use the relative growth rate, right? So number 1 right here doesn't matter at all, right? So it could be limit of n cubed over 4n cubed when n approaches infinity. This guy equals 1 over 4 because this guy cancel out, right? And this guy is a positive and finite numbers, right? So by the limit comparison test, this guy and this guy both either converge or diverge, right? Now we're gonna check this guy to see if this guy is convergent or divergence, right? So we're gonna take limit of this guy 2 to the n over n squared when n approaches infinity. It's gonna be indeterminate form, right? So I'm gonna use last bit rule, right? So it could be limit when n approaches infinity. The derivative of this one is gonna be ln of 2 times 2 to the n, right? Over 2n. And it's still indeterminate form, right? So we're gonna last bit rule one more times, right? So it could be ln of 2 altogether square times 2 to the n over 2. Alright, so this guy actually infinity, right? Not equal to 0, right? So by the n term test, this limit right here diverges, right? So if this guy diverges, the original one right here diverges, right? Now let's move on to question C. So we have 1 over 3 to the n minus n. It's going to be the same thing as 1 over 3 to the n, right? Because they behave the same thing when n approaches infinity, right? So we can call this one as b sub n, right? So we have limit of a sub n is going to be 1 over 3 to the n minus n divided by 1 over 3 to the n when n approaches infinity. Remember this one is a sub n, right? So then it's going to be limit of, I'm going to multiply the top and bottom by 3 to the n, right? So it could be 3 to the n over 3 to the n minus n, right? When n approaches infinity, right? So this one right here grows faster than this guy, right? So we can ignore this guy. So it could be limit of 3 to the n over 3 to the n when n approaches infinity. This guy cancel out, the answer is 1. And this guy is finite and positive, right? So then by the limit comparison test, either a sub n and b sub n converge or diverge, right? Now we're gonna check this guy. So it's gonna be sigma when n goes from 0 to infinity of 1 over 3 to the n. It's gonna be sigma when n goes from 0 to infinity of 1 over 3 altogether to the n. And this guy actually geometric series, right? Where the ratio equals 1 over 3 less than 1, right? And then this geometric series converges, right? Then the original one right here must converge, right? Now let's move on to question D. So we have a sub n equals 4n squared plus n over cube root of n to the 7 plus n cube, right? Now observe that the top is the polynomial function, the bottom still the polynomial function under the radical sign. So they both behave in the same way as the largest power, right? So the largest power right here is 7, the largest power right here is 2, right? So this guy is the same thing as n squared over cube root of n to the 7, right? So I'm gonna rewrite this one as n squared over n to the 7 over 3, right? So I'm going to simplify this one. It's going to be 1 over n 1 over 3, right? And I call this one as b sub n, right? So I'm going to check limit when n approaches infinity of a sub n over b sub n, right? So it's going to be limit of 4n squared plus n over cube root of n to the 7 plus n cube over 1 over n to the 1/3 when n approaches infinity, right? Now I'm going to multiply the top bottom by n to the 1/3, so it can be, now I'm going to multiply this guy by n to the 1/3, so I'm going to end up with, now I'm going to factor n to the 7 out, so it's going to be, now I'm going to factor n to the 7 over 3 out, so I have limit when n approaches infinity, n to the 7/3, it's going to be 4 plus 1 over n, right? I'm going to bring n to the 7 out, so it's going to be n to the 7 over 3, right? Don't forget the cube root right here, times cube root of 1 plus 1 over n to the 4, right? Now this guy right here and this guy right here cancel out, right? So when n approaches infinity, this guy approaches 0, this guy approaches 0, it's going to be 4. This guy actually a positive and finite number L, right? So by the limit comparison test, either both of them converge or diverge, right? Now I'm gonna check to see if this guy converges or diverges, right? So this guy actually the P series, right? Where P equals 1 over 3 less than 1. So this series diverges, right? By the P series test, if this guy diverges, the original one right here must diverge. And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand in mine.